So we have Steve here who's going to start this session with an interesting talk on biostatistics and how it is important for us. So in addition to being a prolific glaucoma expert, Steve has got an MPH from Osho.
Yep,
So he's got very good knowledge on research methodology and how to do quality research. And we have been also involved in studies like antioxidant study and frequency doubling perimetry studies way back in 2000 with Steve. Welcome to AIOC. I'm sure you are having a good time.
Thank you. It's been great to be here, and I really appreciate the organizers for inviting me. I'm a glaucoma specialist in Portland, Oregon, and the goal for this is just to kind of point out what kind of statistics that I see pretty often doing wrong, and then how to get your papers published if you're interested in getting your paper published. So I have no conflicts of interest related to this talk. I hope if you ever get the chance to visit our home in Portland, Oregon, this is the beach where you get these monoliths here in the distance. It's really, really a beautiful place to visit. So I hope you get a chance to come to Portland, Oregon. So these are my topics. I'm going to talk a little bit about the Fisher's exact test versus the chi-square test. Clinical versus statistical significance. We see this quite often with large databases where they'll show a very, very small statistical significance. The analysis of attention to treat versus other. And then some other kind of things that I recommend when you're doing your statistics, such as multivariable. Such as, it's not working. Okay. Such as multivariable analysis with calculated variables, linear and other relationships, and the correlation between eyes. All right, so I have a little bit of a quiz. We don't have a huge group in here, but I have a little bit of a quiz. You have a sample size of 20 patients. What's the appropriate test to compare two categorical variables? And if you don't know what a categorical variable, it's like yes or no, like I have glaucoma, I don't have glaucoma, or I have diabetes, I don't have diabetes. So what's the appropriate test to compare these two categorical variables? Is it a t-test? Is it a chi-square test? Is it a Fisher's exact test? Is it a multivariable linear regression? So that's quiz question number one. Quiz question number two, intention to treat. Does that increase bias? Does that maintain randomization? Does it give data when the surgery has no complications? Or does it bias results towards success? I'll give the answer to this. And then the question is clinical significance versus statistical significance. Is the answer clinical significance increases with sample size? Clinical significance means any p-value below 0.05. Clinical significance may change clinical care, or clinical significance increases statistical significance. Sorry about those long words here. So the chi-square test is based on a normal approximation of the binomial distribution. And many statisticians be a correction for continuity is needed. And this is just basically the equation where the chi-square equals the sum of the observed minus the expected minus 0.5 over the expected. And it reduces the size of the chi-square value. And so it reduces the chance of finding a statistical significance. So the correction for continuity makes the test more conservative. But what do we do if the expected values of any of the cells is below 5? So here's an example of a categorical outcome of interest. Do they have pseudoexfoliation or not? We got men or women. And you can see here we have a cell here where the sample size, or two cells where the sample size is below 5. What Fisher showed that the probability of attaining any of these values was given by this equation. And I'm not going to go through that. So, and basically what he showed is that your p-values will be off if you use a chi-square with such a small sample size. You really need to use the Fisher's exact test. And so when any of these cells are less than 5, you should use a Fisher's exact test. And it's based on the exact probabilities of the specific distribution. There's no formal test statistic and no critical value. It only gives you a p-value. And previously it was very difficult computationally to perform. And so when I have categorical variables, I almost always just do a Fisher's exact test anyway, because it'll work with all of your analysis. And so if you're writing, for example, statistical code in R, you can just run it with your Fisher's exact test for all of your data. And if your data has too much sample size, it's still okay. It works out the same. So what about statistical significance? For some reason, we made this p-value less than 0.05, and that has just been the tradition for statistical significance for many, many years. And we know that it's easier to get a p-value less than 0.05 if the sample size increases. And there's a couple things that we talk about in statistics. One is a type 1 error. And what that means is that it's significant when it's not. So that can happen when you have a confounder in a large data set, like for example, like let's say you're looking at the association of diabetes with glaucoma, and you think the significance is high, but then you look at that group and there's hypertension in that group, and you didn't control for that large confounder. So the type 1 error can happen, and it really makes a difference if that is going to change care. We also see this with detection bias with insurance data sets. You'll see these huge data sets used, and they'll show some sort of significant level. So this is kind of an example of this, that glaucoma, Alzheimer's disease, and Parkinson's disease were all associated with glaucoma. And this comes from a Taiwanese national insurance database. They had 8 years of follow-up. They had a huge sample size of 20,000 patients. And they used 16,000 controls and 4,000 with glaucoma. And what they found was, if they had glaucoma, the incidence of Alzheimer's was 2.85 out of 1,000 person years. And if they didn't have glaucoma, it was 1.98. So the thought is that if you have glaucoma, you're more likely to get Alzheimer's. But you can see it was really a small difference, just a really, really small difference here. And the p-value was 0.03. So the only reason this became statistically significant was because of the large database. If you had another large database in a different country, it may have the opposite result. Then here's a different paper. It looked at Medicare database. This looked at 126,000 patients, and they used an even number of controls in glaucoma, 14-year follow-up, and the probability of Alzheimer's diagnosis was 0.17, and the hazard ratio was less. So here we have a paper that shows that glaucoma is not associated with Alzheimer's, but both are significant, and they have a small impact in opposite directions. So it just kind of goes again with this issue of statistical significance versus clinical significance. What would you do if you had this database? You would look at the power, you would decrease the sample size, just take a random selection of patients and do some sort of reasonable number of patients. When do these large sample size help you? If you're looking for something like a really rare condition, then maybe these large sample size help you. But in a lot of cases, you don't need this large sample size for many of the things that we do in medicine. So the other thing I think it's important about when you're writing your papers, so there's a certain formula. I'm going to go a little bit more over this in a second. So I'm the executive editor for AJO, for the American Journal of Ophthalmology. I review every one of their epidemiology papers. And so I review something like 40 to 50 papers per year. And the reason I can get through so many papers is there's a little formula for getting your paper published. The first paragraph, talks about what's important. Your second paragraph talks about the literature and what's unique about that literature. And the last paragraph will talk about what's unique about your study. And then the very last sentence of the last paragraph of your introduction will say, how will this change care? And so that's a number of rejections that I'll do, is when somebody has something interesting. I just reviewed a paper recently, was looking at antioxidants for causing cataract in children in China. And I rejected the paper because even though the paper was done well, there wasn't anything you could really do about antioxidants in that group for preventing cataracts. And several papers that had already done randomized clinical trials to show that there was no difference. So that's a key part of your writing your papers, is how is this going to change your care? All right, so I'm going to switch gears and go to the intention to treat analysis. For any of you that do surgery studies or looking at outcomes from surgery, this is kind of a really important one. And what you do with this is, like, you'll have somebody, let's say you do, a trabeculectomy, and you're looking at your new technique for improving your trabeculectomy outcomes. And you have a group of patients that come back at 1 week, 1 month, but they didn't come back at 3 months. And so what do? Is you just remove all those patients that didn't come back at 3 months. Well, lo and behold, you do your analysis, and your result did not work out. I mean, your new technique did not work out. But the problem is you remove those patients from the analysis that didn't come back. And what you should do is you should do an intention to treat analysis, where you have statistical ways of taking the data from them and comparing them over time. So in this type of analysis, everybody that is randomized to a group is analyzed in that group. So it's regardless of whether we receive the treatment. So let's say you did a trabeculectomy and you couldn't get the trabeculectomy right and you had to close it, you still do the analysis on this person. It's regardless of their time to withdraw from the study. It's regardless of their deviation from the study protocol. So everybody is analyzed, and the complete outcome data is available for all subjects. It limits the bias and benefit and maintains that benefit of randomization. So here's an example, an intention to treat analysis, a randomized control trial. You've got randomization to either treatment 1 or treatment 2. You've got a group in treatment 1 that for whatever reason didn't get the treatment, and you have the group in 1 that did get the right treatment, and the same thing here in treatment 2. So anyway, you take this whole group and you analyze them as outcome 2, this whole group, and analyze an outcome 1. Again, we see this really common in surgery studies, where they'll remove patients that didn't get the right treatment, or something happened, or a complication. There's also another analysis called per protocol analysis. This is not the intention to treat analysis, and they only take the ones that really got the result or the treatment results. So here's an example from AJO. These patients were screened. They implanted 65 of them. One of them, they didn't fail the screening, and then of these 65, 54 completed the 12-month visit, 11 discontinued, and then they only kept 52 in the performance analysis, and they took these other one out. So what you can see already is you've got a large proportion of these patients that are not even being analyzed by this paper. And these were the results. With this glaucoma surgery, their pressure came down, and then it slowly creeped up over time. And you can also see here what they did is they put the number of sample size here, and you can see the sample size dropping as the time goes on. The weird thing is they call this an intention to treat population, maybe to get the paper published, but it really wasn't an intention to treat analysis. So those are the other common, issue that I see with papers that we reject from AJO very commonly. The other common error that I see is, and many of us in the glaucoma world will know about this variable called ocular perfusion pressure, where you take systolic blood pressure minus diastolic pressure and then divide it by intraocular pressure. And but there's been several papers that show that ocular perfusion pressure is associated with glaucoma. The problem with those analyses is they're not controlling for IOP in those analyses. You've got kind of a variable here that's a combination of 3 other variables. And so if you did the analysis and you controlled for pressure, many of those studies showing that ocular perfusion pressure is associated with glaucoma will not show significance, where what's driving this relationship is the IOP. Same thing with corneal hysteresis. Corneal hysteresis is where you bounce a air off the cornea. You look at how quickly it rebounds from that blast of air, and you can look at whether or not that's associated with glaucoma. The problem with that analysis is that that is highly associated with central corneal thickness and with pressure. And so again, when you take this corneal hysteresis and you're looking at those papers, a lot of those papers will not control for central corneal thickness and not control for IOP, which are already known to be highly associated with glaucoma. So just be careful with these analysis of correlated variables. The other thing that we see pretty often is linear versus other relationships in analysis. So for our visual field analysis, we use, for decibels, that's a logarithmic scale. And there'll be a comparison of that versus nerve fiber layer thickness, which is not. And so you have to get those both in the same scale. Either you log the nerve fiber layer thickness or you do an anti-log of the visual field, and then you can compare those two variables as far as progression of glaucoma. And then finally, the correlation between eyes is something that we see a lot, where people will include both eyes for analysis, or they've done all this work, they've collected the data on both eyes, but they only use one eye for analysis. And there's something called a mixed effects model, which allows you to include both eyes. All you do is you randomize the subject number or the subject name or whatever it is that you're using for that person, and that will control for the correlation between eyes. But if you don't use a mixed effects model, then your data, again, is biased. So just some final recommendations for the statistical analysis. One is I think it's really good to do the analysis yourself, just so you get a feel for what the data is. But you engage a biostatistician relatively quickly in that. Just say, hey, this is what I'm going to do. What do you think? Any problems with this analysis? And they'll give you some great ideas to save you some time. And then do your own preliminary analysis. Many of us will kind of just really jump right into like a correlation analysis or something like that, but really you have to look at your frequency of the data, look for outliers in the data, look for the distribution of the data. Those kind of things are really simple things that you can do with every statistical program, and that will help you understand what the data looks like. And finally, just make sure the data makes sense. Like if you're finding like the results just don't make any sense, go back again to the data and just see if there's something wrong. We've had databases where somebody will make an error and they'll shift the data, and you'll look at the data and you're like, why am I missing 10 results from the database? And you realize that somebody had shifted the database or used an old database. And then writing and reviewing statistics, the analysis should be clear and follow a logical plan. Buy a basic book on statistics. And if you're reviewing papers, if you don't understand the statistics, look it up. But if you still can't understand it, if you look it up, then you can write back to the reviewer or write back to the editor and just say, I can't understand the statistics. You need to, have another person look at this. Okay, so I'm going to give the answers to the quiz questions, and then I'm going to go through a little bit about how to write a good paper. So we already talked about this. This is the N of 20 patients. You have two categorical variables. You want the Fisher's exact test. The intention to treat, what that does is it maintains randomization. So that's why you want to do it. It also helps understand if you get dropouts. You also understands what the results would be even with those dropouts. So you don't have this bias for some patients that stayed in the study. And then clinical significance may change clinical care. That's the important part of that. So if you have something that is really a small difference, like we saw with this Alzheimer's papers, that's probably not clinically significant. Okay, so I'm just going to go quickly over a simple framework for publishing papers. 11 plus, yeah, so I think I have 4 minutes. So this is I have no financial interest in this, but this is a book that I love. I still refer to it after 25 years of writing papers. It's called Successful Scientific Writing by Matthews, Bowen, and Matthews. You can probably get it free on the internet. It's really a great book for writing papers. It'll tell you a whole bunch of things about what to do, like what verb tense to have in the introduction, what verb tense to have in the method section, how to write your first paragraph of the discussion. It's really a useful paper. And I kind of mentioned a little bit about this. I've reviewed at least 1,000 papers for AJO, Journal of Glaucoma, and the number one cause of rejection for these papers is it's unclear how researchers or clinicians would use the results. So as soon as I go through this paper's title and go through the abstract, about 90% of the time, that's what I reject it on. I'm not even though it's interesting, there might be some sort of really unusual association with kidney disease and glaucoma. I'm not sure how we're going to use that as clinicians, so I'll reject that paper. Now, if somebody can say, like, there's some sort of hypothesis about kidney failure and that creates a hormone that might be associated with glaucoma, okay, then that paper might pass that muster, but they have to say how this might change care. And then if there's a whole bunch of papers that already talk about this, then I usually reject that paper because there's already a whole bunch of papers that do this. And then finally, if it doesn't follow some sort of hypothesis testing framework. I kind of gave a little bit about this already. A 3-paragraph introduction is key for your introduction. Why it's important is the first paragraph, and why should the reviewer care. The second paragraph is previous research on this topic. You want to expand or refute that information, like they did this study, but this was what this will improve on. And then your third paragraph, the first sentence is why it adds to the literature. Your hypothesis, we hypothesize that our new antimetabolite is going to improve glaucoma surgery outcomes. And then the last sentence is how clinicians or researchers would use the results. And if you do that, you are 90% of the way on getting your paper published. Your methods, the first paragraph should be study subjects and IRB. Again, this book has this in there. Your middle paragraphs tell the story in enough detail somebody can replicate the experiment. And then you want to put yourself in the reviewer's shoes. If they can understand the experiment, then they're going to be following your paper and they know what to do. And then the last paragraph is just your statistical analysis. Results is pretty straightforward. Basically, you put the most important results first, and you put the findings, maybe in the order of the methods. And then the discussion, the most important part of the discussion is the first paragraph. Explain again why you did the study. So you might take your last paragraph of the introduction, and write that as a first sentence of your discussion. And then how, again, clinicians and researchers would use the study results. You're going to put that in the last sentence of your first paragraph of the discussion. The middle paragraphs kind of expand on the major results. And then the last paragraph gives your limitations for the study, and then what would be some future studies that you would recommend in the future. And that's the formula, I think, for writing a really, really good paper. Some other recommendations. When I was in medical school, I was kind of taught to write passive voice because it sounds smarter. Active voice, where subject, verb, object, that is the way you want to write your papers because it's clearer and it's more succinct. I use an idea tree before I write. I'll write a little circle about what the topic is, and then I'll kind of write an idea tree, which is like how are you going to play out this story about this problem that you're talking about? And it helps make your writing much faster. So I hope I gave you some good ideas about how to improve your statistics in your scientific writing. I hope I gave you a little bit of a formula to improve your scientific writing so it gets accepted. And I hope that you send your papers to the AJO, because I will be looking at them and I'll be like, oh my gosh, they're following the formula, and this paper should be accepted. So thank you very much. And again, I appreciate the committee for inviting me today.
Thank you, Steve. One couple of quick questions. I mean, when you write a paper, where do you start? Do you start with your results methods, or you start with your intro?
Yeah, so the question is, when I'm writing a paper, where do I start? And one of my mentors told me that 1 hour in the library can save you 1 month in the lab. So the first thing you do is you go to the library and you figure out whether somebody's already done this. And if they have, then you've got to restart over and do something else. And then what I like to do, the first thing is kind of present it as a poster at a meeting like this, because you'll write your poster out, your abstract and everything like that. And what I tell my residents and fellows is you can't go to the meeting unless you've got your paper written before you get there. It doesn't have to be perfect, but you have to write it. And so what happens is they write the paper, they present the poster at the meeting, and they'll get some really excellent questions about their poster, and then they'll add that to the paper, and literally they'll submit it a week later. So that's kind of another formula for kind of getting them out. So,
what is your thoughts on generative AI, and is there a role for paper writing? Should we use it or not at this point of time?
Yeah, AI. The question is about using AI to help write your papers. I think I'll tell you, I use ChatGPT all the time, but I use it for some sort of kind of creative writing. Like if I need to write an article for my staff about teamwork, I'll tell ChatGPT to write me a 3-paragraph article about teamwork with a quote. It's awesome. For scientific writing, I've never used it because I kind of have a formula here, and I just don't know how I tell it to do all those things to do it. The other issue with AI is you don't know where it's getting its information. And I just be really cautious, because at least AJO, they'll look at your paper and they'll say how often those words were repeated in other papers. And if they have all these words are being repeated, that paper just gets rejected even before it gets to the editor. So I would say, AI is an amazing technology, and the quote I heard is, those that don't use AI are going to be missing out. So I think all of us are going to be using AI in the future, but just be careful with making sure that it's not taking, writing from somebody else and then gets rejected. So,
how often have you felt bad for rejecting a paper and then it goes to another journal, even a better journal, and gets accepted and it becomes a real evidence, and people are all talking about it?
Yeah. Yeah, it would be embarrassing if I rejected this paper and all of a sudden it gets, lot
of attention.
Yeah, it gets published in a much more prominent journal. And actually the AJO keeps track of that. And I actually don't know what my personal record is, but I have no knowledge of any papers that I've rejected been accepted at like a higher level, journal, maybe ophthalmology. I do have a couple incidences in my 25-year career where I rejected a paper. The author wrote back to the editor and said, hey, he shouldn't have rejected my paper. And then it got sent out again, and one time it got accepted. So I do have that one thing on.
Thank you, Steve.
Yeah, thank you very much.
We appreciate your time and also your trip to India.
Absolutely.
And safe trip back.